Welcome! Today, we're going to unravel a really fascinating chemical mystery. How can one single element wear completely different disguises? This is the whole idea behind a concept called allotropy, where an element can lead a double or even a triple life. So let's just dive right in with a bit of a puzzle. Think about the element carbon for a second. It's the foundation of a diamond, right? The hardest natural substance we know of. But it also makes up the super soft graphite in your pencil that just flakes off onto the paper. So how? How can the exact same element be both unbelievably strong and unbelievably soft? Well, the answer is all in one word: allotropy. So, here's our game plan for this explainer. First, we're going to define what allotropy even is. Then we'll see it in action with three classic examples: oxygen, carbon, and sulfur. And finally, we'll bring it all together to really understand the big picture.
All right, first things first, let's build a solid foundation. What exactly is allotropy?
Okay, here is the absolute key point. We are always talking about the exact same element: pure carbon, pure oxygen, you name it. A great way to think about it is like using the same Lego bricks. The only thing that changes is how you snap those bricks together. A different arrangement creates a totally different structure, and that leads to materials with wildly different properties.
Let's make this real with our first example. This is an element that is literally all around us, keeping us alive with every single breath we take.
So on one side you have O2. That's two oxygen atoms bonded together. This is the stuff that makes up about 21% of the air we breathe. It's stable, and it's essential for life. But what if you add just one more oxygen atom? Then you get O3, which you probably know as ozone. This three-atom structure forms a vital shield way up in our atmosphere, protecting all of us from the sun's harmful UV rays. See? Same element, just a different structure, leading to two completely different and equally critical jobs.
Okay, now let's turn to carbon, which is, without a doubt, the superstar of allotropy. The sheer variety of forms it can take is one of the most incredible examples in all of chemistry.
This table really tells the whole story, doesn't it? It just highlights the incredible range of what carbon can do. I mean, just look at hardness. Diamond is the hardest material there is, while graphite and buckyballs are soft. Then you look at electrical conductivity. Diamond won't conduct at all, but graphite is a really good conductor. It's a night and day difference, and it all comes down to one thing: how those carbon atoms are arranged.
So, first up is diamond. Its legendary hardness, that incredible sparkle, it all comes down to its unique and unbelievably strong atomic structure. You have countless atoms linking up to form what is basically one giant, perfectly ordered molecule.
So what's its secret? Well, inside a diamond structure, every single carbon atom is bonded tightly to four of its neighbors. This creates this massive, rigid, three-dimensional lattice. There's just no room for anything to move. And that's what makes diamonds so incredibly hard. And because all its electrons are locked into these bonds, they can't move around freely either, which is why diamond is not going to conduct electricity.
All right, now let's meet carbon's polar opposite, graphite. It's also made of pure carbon, but as you're about to see, its properties could not be more different.
You've almost certainly used graphite today. You know the lead inside your pencil? Well, surprise, it's not lead at all. It's graphite. And the whole reason it works so well for writing is that its structure is soft enough to just rub right off and leave a mark on the paper.
So what makes it so soft? Well, unlike that 3D network in diamond, graphite's carbon atoms are arranged in these flat hexagonal sheets. Think of them like stacked pieces of paper. The bonds holding the sheets together are really weak. This means the layers can easily slide past one another, which makes graphite feel soft and slippery. And because those bonds are so weak, there are some electrons free to move between the layers, and that's why graphite can conduct electricity.
And now for a more modern member of the carbon family, the buckyball. Its official name is a bit of a mouthful, Buckminster fluorine, but it has this really cool, unique, cage-like shape that looks just like a soccer ball.
The most common type, C60, is made of exactly 60 carbon atoms arranged in a pattern of hexagons and pentagons, and that creates a hollow sphere. This little molecular soccer ball is a soft solid, it has a low melting point, and a lot like diamond, its electrons are held pretty tightly in place, so it's not a great conductor. This unique hollow shape has scientists really excited about all sorts of potential uses, from delivering medicine to creating new kinds of electronics. So we've seen how carbon can form these vastly different, really stable structures. But what happens when you bring external conditions, like temperature, into the mix? Well, our final example, sulfur, introduces this other really important idea in allotropy, the concept of stability.
At room temperature, sulfur has two main allotropes, which are basically just different crystal shapes. You can think of them as different ways the sulfur atoms like to stack together. We call them rhombic and monoclinic sulfur. Under normal everyday conditions, the rhombic form is the more stable arrangement. It's kind of like the atom's most comfortable state.
Now here's where it gets really interesting. Temperature can actually make sulfur switch between its forms. If you heat up rhombic sulfur past about 96 degrees Celsius, you give the atoms enough energy to break their formation and rearrange into that less stable monoclinic structure. But then, if you let it cool back down, it'll slowly transform right back into the more stable rhombic form. It's a totally reversible change, all controlled by temperature.
Wow, okay, we have covered a lot of ground, from the oxygen in the air to the graphite in your pencil. So let's just take a moment to summarize the big ideas you should really take away from all this.
If you only remember 3 things from this explainer, make it these. First, the definition. Allotropy is simply one element existing in multiple forms. Second, the reason it all matters. The arrangement of the atoms, the structure, is everything. It determines all the properties. And third are key examples, oxygen, carbon, and sulfur, which are perfect showcases of these principles in action.
And that leaves us with a final and pretty exciting thought. Understanding allotropy isn't just about passing a chemistry test. It's actually the key to the future of material science. If we can learn how to control exactly how atoms are arranged, we could potentially design brand new materials with incredible, tailor-made properties, all from the common elements we already have. Just imagine the possibilities.